Thank you for the introduction. Me and the organizers for putting together this very beautiful conference. Thank you for giving me the opportunity to talk today about some of our efforts in assembling and probing synthetic quantum matter photons using superconducting circuits. And this work I did during my postdoc at the University of Chicago in the Schuster and Simon groups. They're currently in Stanford. So the motivation behind these experiments follows kind of this growing interest of understanding strongly correlated materials, both from a fundamental perspective of understanding phenomena in this matter models, as well as harnessing these technologies, harnessing these quantum systems for technological applications. Now, for large system sizes, these models are hard to simulate on a classic computer, so there is a growing interest in growing effort in engineering quantum systems where you can controllably simulate the quantum phenomena of interest. And experimental progress has made it possible to characterize and manipulate individual quantum systems in a lot of platforms. And today I'll talk about using interacting microwave photons in superconducting circuits. Okay, so as is currently discussed, and will be discussed in this workshop, quantum simulation follows generally two approaches, both with their own advantages and disadvantages. You have the digital approach that promises a universal simulator where the efficiency of your Trotter representation relies basically on having small gate errors. Zlatko has discussed in the previous talk some strategy on how you can mitigate these errors. And then you have also the analog approach that relies on basically implementing the model directly in the lab. And it's not as versatile as a digital simulator, but if you can implement this model Hamiltonian, this approach is less prone to errors and holds great promise for performing these types of simulations with current noisy hardware. And the research we're interested in is in building analog quantum simulators with superconducting circuits. And the circuit community, this is where the circuit community has developed a lot of the critical pieces for building synthetic quantum materials with microwave photons and quantum simulation in general. To save some time, let me just briefly describe the quantum system that our work is based on. We're implementing a one-dimensional Bose-Hubbard model for microwave photons. The idea is that we want to pattern an artificial lattice where photons can tunnel and have an effective mass similar to electrons in a solid, and also a way in which they can experience strong on-site interactions. And this competition between kinetic energy and strong particle collision essentially will give rise to strong correlated phases, such as a Mott insulator and a superfluid. And to understand how we actually synthesize this material with superconducting circuits, let's start from our basic building block, the single lattice site. And since we're dealing with bosons, it's natural to use a microwave oscillator to represent the single lattice site. And the simplest oscillator you can make in the lab is an LC circuit. And in order to introduce photon interactions, the easiest thing you can do is basically replace that inductor with a Josephson junction. And the nonlinearity of the Josephson junction basically gives you, as I'm showing here, an anharmonic energy spectrum. You can think of it either as a particle quantized in a cosine potential, or you can think of this Josephson junction acting as a nonlinear inductor, where every time you put in an extra photon or extra quanta, it changes the inductance and therefore changes the energy structure and makes it anharmonic. Now, this is obviously important for quantum computing as it allows you to operate the circuit as an effective qubit and perform operations on the lowest true energy levels. And in our platform, we harness this anharmonicity to generate an effective on-site interaction strength between the photon, as this provides a clear large energy cost for introducing an additional photon in the system, as shown in this spectroscopic measurement, where you can see there's a large frequency difference or energy difference if you go from no photon to one photon versus one photon to two photons. Okay, and how do we couple these two lattice sites? Well, we can couple these circuits directly simply through a capacitor, and this allows the photons to coherently tunnel from one lattice site to another, as shown in this experiment, where you put a photon in one qubit or one lattice site, and then we can see coherent oscillations because the photon goes back and forth between two qubits. Then we can combine these two ingredients, and we can realize a platform of one-dimensional Bose-Hubbard model, where the qubits, called these transmon qubits, shown here as blue crosses, they correspond to the lattice sites, where photons can tunnel between the lattice sites and experience strong on-site interactions because of their anomalisity. Once we fabricate our circuit, the tunneling strength as well as the interaction strength, they're fixed as you lithographically define your circuit. The only thing that you have control over, as I explain later, is the on-site disorder, or basically you have real-time control of the potential landscape of your artificial material. Okay, so here I'm showing you the full picture of our device. I already described time-binding chain transmon. This is basically where the science happens. And one thing I glossed over is the fact that each qubit has not one just junction, but two just junctions in a loop. This is a super quantum interference device. And by inductively coupling the qubits to flux bias lines, this allows you to change the effective Josephson energy, therefore its effective inductance, and therefore you change the resonance energy of each lattice site. And basically, this is what I mentioned before, this is how you have real-time control of the disorder, or you have real-time control of the potential landscape. This is a strategy that I'm going to show we're going to use later for state preparation. Then we can perform site-level microscopy by coupling each qubit off-resonantly to microwave oscillators, and this allows us to basically probe the on-site population of the lattice sites by simply probing the resonators and probing basically the dispersive shifts. The dispersive shifts basically maps to the qubit's internal degree of freedom. Either you have a photon, don't have a photon, or even measure the populations. Okay, and to briefly show you what are the parameters in our circuit, we have our lifetimes, our tunneling times are around 3 orders of magnitude larger than our lifetime, so we can have quantum coherent evolution, and our interaction strengths are about another order of magnitude stronger, so this is how we have basically hardcore bosons confined in one dimension. This is a growing field where many research groups are building Hubbard models from circuits, and putting these ingredients together to get your target Hamiltonian is just the beginning of the journey, because what is equally important, and actually is very challenging, is to prepare entangled states in a large quantum system. Because even if you can do it, let's say, how can you actually tell that you did it? And these problems are actually, these many bar problems present a central challenge in quantum science, and they're hard to do because they scale exponentially. And this has been a major theme of our research. We have been working on developing various preparation protocols and new types of probes in these types of materials. And in these last few minutes, I'm just going to briefly highlight our efforts in using the sorter to prepare strong correlated photon fluids, and how we can also use site-resolved control to also prepare our lattice in the superposition of being a solid and a fluid, and how it connects to an entangled Newton state, and then how we can use Ramsey interferometry with a single qubit to probe entanglement in these systems. So briefly, let me just say the way we prepare our quantum fluid is we leverage the sorter. The way we do that is shown in this diagram. We detune our qubits far enough in energy such that we suppress the tunneling, such that the states in the large disorder limit, they're just product states where the photons are localized in each lattice site, and the way we put the photons is basically we just apply calibrated pi pulses. Then we slowly evolve the system in order to maintain a uniticity, such that we're following the same instantaneous eigenstate, and then we're removing the disorder to near degeneracy, where due to quantum-induced tunneling, we get the strongly correlated fluid, and at the end we do site-resolved probe of density, correlations, and also coherence. So as a warm-up, we benchmark the system by preparing single particle states in a box. So we start from a large disorder limit where we have a photon localized on one side. We dramatically evolve the system, and it delocalizes into quasi-momentum state, and because into uniticity, there's a clear one-to-one correspondence between where we put our photon and which quasi-momentum state we delocalize into. And this is just showing the data of the density evolution. We start localized, and then we delocalize into a sin kx time state. And then, the way we, I'll just mention this fast, the way we can benchmark atypicity is by simply, instead of doing tomography of the final state, we can reverse our RAM protocol and we can quantify atypicity just in terms of what is the efficiency in which we can recover our initial state. And we vary the ramp rate over 4 orders of magnitude, then we can reach some target time in which we can recover our information. We can say that we've, to the best of our applications, we can exactly melt the particles. And then we can also do the same protocol for melting multiple particles as shown here. We can remove the disorder, and we see the localized particles delocalize into our quantum fluid. We can do this for 2, 3, and 4 particles. One interesting feature that we see is that the density profile has a striking dependence on the total number of particles we have in our system, and this is already offering some insights into how the photons order themselves as they're confined in 1D and they're experiencing strong interactions. Interactions obviously play a big role because if you have no interactions, all the density profiles should just look the same, similar to the single particle case. But if we just take our many-body wave function, where we have contact interactions, then we can see that our theory matches very well our experiment. And this is just saying that clearly interactions are really reflecting and shaping the profiles of the fluid. And one way we can actually probe the order due to delocalization interactions is one thing we do is by measuring spatial G2 to probe the order of the fluid by measuring the spherical correlation function, where you basically quantify the mobility of simultaneously detecting 2 particles, some space x apart. And this is the data showing you for all the density profiles. It matches nicely a parameter-free, disorder-free Thompson-Jordan model, where we can see that the anti-punch images scales with density, just because as you put in more particles, they have less space to delocalize into. But we can also see small hints of Friedel oscillations that shows you that if the photons are confined, they're confining the quantum fluctuations in 1D and having strong onset interactions, they're basically behaving as free fermions. So, just this last thing I want to point out is that we're also trying to think of ways in which, okay, we initially started by the qubits, they're decoupled in some product state. We adiabatically evolved the system to prepare some entangled fluid, but if we adiabatically come back to the same configuration, we're going to recover the same boring product state. So one question we want to figure out is, can we leverage our synthetic material and dynamics in this system to generate the highly entangled state when we decouple the qubits? And how can we verify we did? So the way we do this protocol is basically we engineer our disordered configuration in this fashion where the qubits on the left are the highest energy, and we have an ancilla qubit in the middle. And we melt the system where not all the qubits are degenerate, but we have that our ancilla qubit has its second excited state accessible to the other lattice sites. And in this configuration, if we adiabatically evolve the system back into a reverse staggered configuration where the right-hand qubits are at a higher energy or higher frequency, if the ancilla qubit is empty, nothing happens. It'll always come back with the photons on the left-hand side. But then what happens if our ancilla is occupied? Well, we can see that now the second excited state is available to the lattice. So as we melt the particles, they melt into a fluid, and as we adiabatically come back, we now have all the photons go on the right-hand side. And you probably already found the punchline, which is what happens now if our ancilla is in the superposition of both ground and the excited state. And by doing this conditional melting preparation scheme, we can now prepare our lattice in a coherent superposition of being both in a solid or a compressible phase if the ancilla is in the ground state, and in a fluid phase if the ancilla is in the excited state. And if we come back to our disordered configuration, this is how we recover our highly entangled new state. Now, how we can tell we did it? Well, the thing is, I'm an engineer by heart, so I like to be a bit greedy. So not only do we use this ancilla to have this conditional state preparation, but we're going to also measure the Ramsey fringes, the Ramsey spectroscopy arm of our ancilla to probe entanglement. And here I'm showing you what is the bare Ramsey fringe of the ancilla if there was no entanglement. And if we entangle our system, we see that these Ramsey fringes oscillate much faster. And they oscillate at a detuning that actually corresponds to the energy difference between the two configurations that you're entangling. And this is shown in the Fourier transform. You can indeed see that these two Ramsey peaks are apart by what you would expect. And then again, this just brings On the point that you can access many byte information from Ramsey interference of a single qubit, where again, the frequency tells you the energy difference of the configurations you're entangling, and the fact that you see oscillations, a clear fact that you have a coherent entanglement state, that you have coherence. Another thing is that just because it's oscillating faster, you'd also like to tell that you have the right entangled state. And one thing we do is we also detune the sites by intentionally adding additional disorder and see how this main body Ramsey peak shifts as a function of our disorder. And we see that indeed the peak shifts or our immune state is sensitive. The sensitivity scales with the system size. The slope goes with the number of qubits that you entangle. So with that, let me just summarize. I presented some new preparation techniques and new types of probes. In our Hubbard model, we're hoping that as we scale the complexity of our system by going to longer range tunneling or longer range interactions, we can probably use these same preparation schemes to look at even more exotic states. With that, let me acknowledge the team, the Schuster Lab, the Simon Lab teams, our quantum simulation team, Brendan, Gabrielle, and Meg. Gabrielle is here. I actually encourage you to go and see our poster where we can use the Ramsey interference scheme to measure compressibility and chemical potential in these fluids. I'd like to acknowledge our theory collaborator, Caitlin, and right now we're kind of in the transit stage where my PIs have already moved from Chicago to Stanford, and I'll be starting a research group at NYU. So with that, thanks for your attention, and I'm happy to answer any questions now or during the questions.